Good morning, Professor. Hopefully, you will be fine. Everything is fine here too. First of all, thank you very much for your time and consideration. So, now I would like to introduce myself very briefly. My name is Fazli Karim. I'm married, having three school going kids, and currently working as assistant professor at the Department of Civil Engineering, Sarhad University, Ring Road, Peshawar, Pakistan. Now, I would like to briefly describe my educational background and research activities. I have done Bachelor of Civil Engineering in 2004 from University of Engineering and Technology, Peshawar, Pakistan. I have also been graduated from the Royal Institute of Technology, Stockholm, Sweden in 2009. I carried out my master thesis under the kind supervision of Dr. Ilva Edwards on the effect of takeout on interlayer bonding in asphalt pavements. The study basically consisted evaluating interlayer bond strength using various factors such as take coat type, take coat application rate, the recurring time, dilution rate, binder content, temperature, existing surface condition, particularly of the interlayer bond between asphalt binder cores and asphalt wearing cores. I have recently completed my PhD studies in 2022 from University of Engineering and Technology, Texala, Pakistan. And my study basically consisted, or my research basically consisted, estimation of asphalt binder film thickness in the conventional and recycled asphalt mixture using micro level techniques. Now, I would like to share my research area. So, asphalt binder film thickness. As you know, sir, asphalt is basically a mixture of coarse aggregate, fine aggregate, filler, and bitumen, and usually mixed in the asphalt plant at a particular temperature based on viscosity of the binder. And after mixing, the materials are usually transported to the site, placed, and thoroughly compacted to the desired density. So, in a hot mix asphalt, some of the bitumen is usually absorbed by the pores of the aggregate, which is called absorbed asphalt, and some of the bitumen is used to produce a coat of bitumen on the aggregate surface, thereby lubricating the grains in the asphalt mixture. And this binder content is called effective asphalt, and the thickness of the effective asphalt is called asphalt binder film thickness. So the current research is totally linked to the asphalt binder film thickness in asphalt mixture. The asphalt binder film in the asphalt mixture is also termed as an interface bonding agent or adhesion promoter. And its prime objective is basically to provide structural integrity among the aggregate in asphalt mixture so that the asphalt mixture may withstand traffic and environment. The schematic diagram of asphalt mixture containing three aggregates has been shown where asphalt binder film on the surface of aggregate has been shown. Now, the current research was basically based, and every research is usually based on some problem area or literature gap, and therefore a huge literature was basically studied, and all the film thickness is required for best performance of asphalt mixture so that the VMA criteria can be replaced was tabulated. But while looking at this table, it is very difficult to follow a particular limit of asphalt binder film thickness to be followed for asphalt mixes so that the VMA criteria design can be replaced. According to, I would like to briefly describe, according to MacLeod, that is 8 micrometer. But according to Robert, 8 to 15 micrometer. According to Kendall, 9 to 10. We also have 6 to 8 micron, but no background research data is available to support these values. And similarly, according to Heitzman, 9 to 15.5 and Oliver, 7.5 micrometer. So while looking at this table, it's a bit confusing. Or we can say there are discrepancies in these values. Now the question is that where do these values come from? So these values have been assessed using these analytical models. And to date, the estimation of asphalt binder film thickness is based on these analytical models. And these models, as per studied literature, are based on various assumptions like sphere shape aggregate, uniform binder film thickness around the aggregate in asphalt mixture, and no clarification on porosity and magnitude of compaction in asphalt mixture. So the inaccurate measurement of asphalt binder film thickness and the consequences of not having adequate film thickness model has substantially introduced discrepancies in predicting actual performance of asphalt mixture. The basic concept is that the values of film thickness have been assessed, but the models are based on assumptions. But however, due to development in state-of-the-art equipment and super specification, the asphalt binder film have been studied on micro level, and viscosity has been declared as important criteria for the mixture performance. And to my knowledge, the asphalt binder film thickness has not been studied on micro level. The effect of temperature and binder content has not yet been calculated at micro level. And therefore, the current study was basically aimed at investigating the asphalt binder film thickness at micro level so that the validity of the aforesaid equations can be checked. So therefore, mixed design was basically carried out at 3 different temperatures, 140-degree, 150-degree, and 160-degree centigrade, for the binder content ranging from 3.5 to 5.5%. So after calculating volumetrics, the asphalt binder film thickness was calculated using these analytical models. And the film thickness ranges from 9.88 to 12.46. Now, these are the film thicknesses assessed analytically for the mixed design carried out at 3 different temperatures for the models shown. Now, the next phase was basically to check validity of these film thickness using micro level techniques. Therefore, GL GSM IT100 scanning electron microscope available with sputter gold coater was used at magnifying power ranging from 250 to 30,000 and bar scale of 100 to 0.5 micrometer. The Marshall specimen were basically sliced in order to visualize the internal micro details of the asphalt mixture, and the required specimen size was basically obtained. Then a point of interest was basically designated on this specimen, and a coat of gold was also applied on the specimen so that the micro details can become visible during morphological analysis using micro level equipments. So these are basically images of the asphalt sample when mixed design was carried out at 140 degrees centigrade, and optimum binder content for this mixture was 4.36. So the analytically values have already been assessed. So now currently we were trying to measure asphalt binder film thickness. So this is basically the image of asphalt mixture at magnifying power of 200 and bar scale of 100 micrometer, and asphalt mortar, which is a mixture of bitumen, fine aggregate, and filler, have been shown. And this asphalt mortar is particularly used to grip larger aggregates. Same asphalt mortar. Here, we can see filler particles in asphalt mastic, asphalt mastic is basically a mixture of, or we can say asphalt mastic is a two-phase system containing bitumen and mineral filler. Similarly, we can say blurred asphalt binder film thickness, which is clearly visible in the next slide. So now this is clearly visible asphalt binder film among the filler particles, and when the image was taken at magnifying power of 30,000 and bar scale of 0.5 micrometer. And now I would like to say that asphalt, pure asphalt binder film only exists in the asphalt mastic. Wherever we went in the asphalt mixture, we couldn't find pure asphalt binder film. The only place where we found asphalt binder film thickness is asphalt mastic. Now, in order to verify the existence of pure asphalt binder film, a point X was basically marked and elemental composition of the asphalt binder film was determined. And we found in this configuration only the elements of bitumen, which guaranteed that the existing cover is really that of bitumen. Now again, the images of Marshall, specimen when the mixed design was basically carried out at 150 degrees centigrade, optimum binder content 4.23%. Again, asphalt mortar, again mortar, and filler particle in asphalt mastic. And this is basically asphalt binder film ranging from 1 micrometer, 0.5 micrometer to 1.2 or 1.7 micrometer. Again, clearly visible asphalt binder film in the range of 1.3 to 2.35. Again, XRD was conducted to clearly indicate the existence of pure binder film. Again, ACM images of the mixed design at 160 degrees and optimum binder content 4.12%. Optimum binder content also vary with temperature. Asphalt mortar, these are basically filler particles in the asphalt mastic. And so one of the interesting, finding of the study was this emptiness or earwides, the existence of emptiness or earwide even among the filler particles in asphalt mastic. This is basically filler particles of the mastic at another location of the sample. And this is clearly visible asphalt binder film. Again, due to shortage of time, I just, I have selected a few images for current presentation. The detail is already there available in the articles published. So again, XRD was basically conducted to show the existence of pure binder film. Similarly, all the film thicknesses, concluded from image analysis were tabulated in this table. This is basically different binder content, optimum binder content at various temperature for 3-mix design, and these are film thicknesses. And almost it exists in the same range. At 140 degrees and 0.5 to 2.4, here again 150, 0.5 to 2.35, and again 0.5 to 2.24. And these film thicknesses can be trusted because the images are very clear and indicate what really happens in the sample and what is the possible range of binder film thickness. Now, there is a hell of difference between these values. The micro-based or the film thicknesses basically vary from 0.5 to 2.4, where the film thickness is based on analytical models are, ranging from 9.88 to 12.46. So there is a huge difference. Therefore, a statistical factor was basically developed, a transformation factor was developed so that the values, so that the analytically assessed values can be transformed into the range of film thickness measured during micro level techniques. So These are the design, because the next phase was basically to measure binder film thickness in the recycled mixture. So therefore, recycled mixture were prepared containing 40% rape, 50% rape, and 60% rape. So, and these quantities were selected with the intention so that the rape quantity in Pakistan can be expanded. So similarly, all the volumetrics were basically calculated. But as you know that for aged asphalt, some rejuvenators are required to be used so that uh, it may complete the percentage of saturate, aromatic resin, and asphaltenes. So using these recycled mixture and rejuvenator, all the volumetrics were calculated. And the next phase was basically to calculate binder film thickness in the recycled mixture using these volumetrics. So therefore, asphalt binder film thickness was basically assessed for each rejuvenator content and each percentage of recycled mixture using these analytical models. Now, the next phase was basically to verify these film thicknesses, which has been tabulated by using micro level techniques. Therefore, again, all the samples were thoroughly studied using scanning electron microscope. 40% recycled mixture with 3% rejuvenator, 50% recycled with 6% rejuvenator, and 60% recycled mixture with 9% rejuvenator content. So all these images basically show asphalt mortar gripping large aggregate and asphalt mixture. Similarly, all these images basically show asphalt mastic, reflecting filler particles. Even flaky, elongated, and round filler particles can be seen even with emptiness in the asphalt mastic. And here, asphalt binder film can be seen among the filler particles. And now, here, clear asphalt binder film thickness in each type of mixture is visible. Usually in here, ranging from 0.4 to 1.6, similarly 0.8 to 2, and similarly 0.4 to 1.8. All these images are almost in the same range, but one thing has been observed, that the film thickness measured in the recycled mixture is a bit smaller than the film thickness measured in the conventional mixture, and it's because of aging process, because the aged material were collected from a road which has already survived for 15 years. So that's why uh, the film thickness is a bit smaller than conventional. And similarly, here a point A was basically selected so that XRD can be conducted in order to detect the presence of pure binder film, just like the conventional texture. And this is basically elemental composition of asphalt binder film at point A, which basically guaranteed the existence of pure binder film. Similarly, a point of asphalt mastic was also chosen at point B, and XRD was basically conducted. And all the elements in the configuration basically reveal the existence of pure asphalt mastic. Now, this is another factor, transformation factor developed for the recycled mixture, so that the values of, film thickness based on analytical models can be transformed into the value of film thickness based on scanning electron microscope. Now, the association between SEM-based asphalt binder film thickness and average model-based asphalt binder film thickness computed using analytical model was displayed as a linear function with R square of 0.947 and a polynomial function of order 2. Polynomial function of order 2 having R square of 0.982. So these models, new model have been developed, which will be used to transform the analytically assessed film thickness into the value of film thickness based on image analysis. So these are some of the findings. The analytical estimation revealed that the asphalt binder film thickness in their conventional asphalt mixture under all conditions of temperature and binder content varies from 9 micrometer to 13 micrometer with a fair relationship to binder content and mixing temperature. However, however, so sorry, as a result, future, I'm sorry. However, results obtained from image analysis reveal that the asphalt binder film thickness varies from 0.5 micrometer to 2.4 micrometer with no relation to binder content and mixing temperature. While looking at analytical values, the film thickness varies from 9 micrometer to 13 micrometer with a strong association to binder content and temperature. But while looking at the values of film thickness measured using SEM, the range is 0.5 micrometer to 2.54 micrometer with no relation to binder content and mixing temperature. The asphalt binder film does exist as a separate entity only inside the asphalt matrix around the filler particles as a non-absorbed binder in the form of a band which fills the approximate distance of 0.5 to 2.4 micron among filler particles. So these were some of the findings. Research plans. As already described that the asphalt binder film basically, exists as a non-absorbed binder which fill the approximate distance of 0.5 to 2.4 micrometer. Although in current study, the effect of temperature and compaction was basically measured, but the effect of compaction was basically beyond the scope or beyond the target area. So, but because in our study, the compactive effort was basically constant, but the visual examination and knowledge gathered throughout the research activity theoretically suggested that the film thickness could be a function of compaction in conjunction with temperature. As a result, future research should focus on film thickness under various temperature and compactive effort circumstances, implying image analysis technique and analytical models. The future research should contain the study of various type of additives in novel asphalt mixture, like various additives which have been shown like nanoparticle, like nanoclay, nanosilica, nanotubes, crumb rubber fibers such as cellulose, glass, steel, synthetic fiber, and some eco-friendly material like sessobet in combination with cellulose fibers. But the one which I personally use here in my laboratory is nanoclay and crumb rubber. In order to, improve the performance of asphalt cement, the nanoclay is basically used as per dry method, and the crumb rubber I use as per wet method. And both of them are basically used to improve performance of asphalt mixture. But here, I would like to describe that sometimes it is very difficult to detect the distribution or the presence of nanoclay or crumb rubber in the asphalt cement or asphalt mixture during, micro level study. It's very difficult to detect. Therefore, I personally use nano titanium oxide. Titanium oxide basically serves multi-purposes. It can either be used in the powder form or it can be melted and can be used in the liquid form. So number first, it is basically a catalyst which speed up the rate of reaction. Number two, it is antioxidant, which basically retards the aging process of asphalt. And the most important thing is that it can be used as a tracer. Sometimes when we want to easily detect nano clay particles or crumb rubber or the diffusion of crumb rubber when we use as per wet method in the asphalt mixture, I use TiO2. So TiO2 on one side improve the performance, but on another side it basically form a coat or cover around the crumb rubber or nanoclay particles and help help to be detected during SEM process. Because when it form a cover, then SEM process, during SEM process it is usually detected by yellow band, and it basically easily let us know the extent up to which nanoclay or crumb rubber or any kind of additive can diffuse. So it is also very good for to detect the extents of distribution of additive in the asphalt cement or even in the asphalt mixture. And for the micro level studies, actually, we use X-ray spectroscopy, scanning electron microscope, and also high performance liquid chromatography is also sometimes very essential. As you know that aged asphalt is basically lacking. Recycled asphalt is basically lacking saturate aromatic resin and asphaltenes, and therefore I personally use various type of rejuvenators in the aged binder so that we can bring life to the aged binder, which basically, and these rejuvenator basically enhances the percentage of SARA components, saturated aromatic resin and asphaltenes in bitumen. And here again, TiO2 I personally use for the rejuvenator, which basically produce a coat around the rejuvenator, and then wherever it goes in the bitumen, that can be easily detected. So thank you very much for your valuable time. I would welcome any kind of question. Thank you, sir.